Assalamualaikum and good day everyone. My name is Siti Aisyah binti Muhammad Isham. My matrix number is 207026. Today, I'm going to present about fluid features and dimensional analysis concept. For part A, fluid features, which cover about introduction to fluid properties, Newtonian and non-Newtonian fluids, surface stretch and elastic modulus, and also compressibility of fluid and vapor pressure. For part B, dimensional analysis concept, which cover about dimensions and dimensional homogeneity, dimensional analysis and similarity, the method of repeating variables, and the Buckingham Pi Theorem. And lastly is dimensionless terms. Before that, what is fluid mechanics? Fluid mechanics is the study of the behavior of fluids, either at rest, fluid statics, or in motion, fluid dynamics. Fluids can be either liquids or gases. Liquids are only slightly compressible, while gases are readily compressible. I will explain more about compressibility later. Fluids can be characterized by their physical properties, which are density, specific weight, specific gravity, surface tension, and viscosity. These five are the properties of the fluids. The first property is density. Density is the amount of mass per unit volume of a substance. This is the formula rho is equal to mass over volume, and the unit for density is kilogram per meter cube or slugs per feet cube. The second property is specific weight. Specific weight is the amount of weight per unit volume of a substance. The formula is gamma is equal to weight over volume. The unit is Newton per meter cube or pound per feet cube. Next is specific gravity. Specific gravity is the ratio of the density of substance to the density of water at 4 degrees Celsius, or the ratio of specific weight of substance to the specific weight of water at 4 degrees Celsius. The value for density of water at 4 degrees Celsius is 1000 kilogram per meter cube or 1.94 slugs per feet cube. And also, the value for specific weight of water at 4 degrees Celsius is 9.81 kilonewton per meter cube or 62.4 pound per feet cube. The fourth property is surface tension. Surface tension is the energy required to increase the surface area of a liquid by a unit of area. The formula for surface tension is equal to work over area, and the unit is Newton per meter or pound per feet. I will explain more about surface tension later. Okay, the next property is viscosity. Viscosity is defined as fluid's resistance to flow. As you can see here, if the fluids flow or pour easily, means it has low viscosity. If the fluid's hard to flow, means it has high viscosity. There are two types of viscosity, dynamic viscosity and kinematic viscosity. For dynamic viscosity, denoted by this symbol, eta or mu. But in our reference book, we use this symbol, which is eta. Dynamic viscosity, also known as absolute viscosity. Shear stress, tau, is defined as the force required to slide one unit area layer of a substance over another. Shear stress will develop in a fluid as the fluid is moving. And the formula for shear stress is equal to force over area. The unit is Pascal or Newton per meter squared or pound per feet squared. Also, shear stress is equal to dynamic viscosity times with velocity gradient. As I said just now, shear stress will develop in a fluid as the fluid is moving. And as the fluid is moving, it causes the velocity gradient to be created in the fluid. Velocity gradient is a measure of the velocity change, also called as shear rate. Dynamic viscosity is the measurement of the fluid's internal resistance to flow. The formula for dynamic viscosity is equal to shear stress times with velocity gradient. We just rearrange from this equation. The unit for dynamic viscosity is Pascal second or Newton second per meter squared. or kilogram per meter second. Next is kinematic viscosity, denoted by this symbol. We call it as mu. Kinematic viscosity is the ratio of dynamic viscosity to density. So the formula is mu is equal to eta over rho. The unit for kinematic viscosity is meter squared per second. Okay, next is Newtonian and non-Newtonian fluids. Newtonian fluids is fluid in which viscosity remains constant no matter amount of shear stress applied for constant temperature. As you can see here, Newtonian fluids, it has a linear relationship between shear stress and velocity gradient. The example for Newtonian fluid is water, glycerin, mineral oil, kerosene, gasoline, benzene, and alcohol. Next is non-Newtonian fluid. Non-Newtonian fluid is fluids in which viscosity changes when shear stress is applied. There are two major classifications for non-Newtonian fluids, which are time-independent and time-dependent. For time-independent, we have dilatant fluids, pseudoplastic, Bingham fluids, and for time-dependent, we have thesautropic fluids and also rheopathic fluids. Time-independent means the viscosity at any given shear stress does not vary with time. Dilatant fluid, as you can see here, the graph for dilatant fluid, the higher the shear stress is applied, the slope increases with increasing velocity gradient, means it has higher viscosity. The example for dilatant fluid is starch in water, titanium dioxide, and quicksand. For pseudoplastic, as you can see here, the pseudoplastic graph, the higher the shear stress is applied, the slope decreases with increasing velocity gradient, means it has less viscosity. Example for pseudoplastic is blood plasma, syrups, ketchup, and inks. Next is Bingham fluids, or also known as plug flow fluids. For Bingham fluid, as you can see here, it requires development of a significant level of shear stress before the flow will begin. Once the flow starts, there is a linear slope indicate constant viscosity. Example for Bingham fluids is chocolate, mustard, mayonnaise, paint, and toothpaste. Next is time dependent. Time dependent means the viscosity vary with time. On the left part of the curve show stable viscosity when shear rate is not changing. Then, when the shear rate changes, the viscosity also changes. Rheopathic fluids, as you can see here, viscosity increases with time when shear is applied. The example for rheopathic fluids is gypsum paste and cream. For thesautropic fluids, the viscosity decreases with time when shear is applied. Example for thesautropic fluid is paint, glue, asphalt, and cosmetics. Next is surface stretch and elastic modulus. I will explain about surface stretch first. Okay, surface tension is the tendency of the surface of a liquid to behave like a stretched elastic membrane. The molecules on the surface of a liquid, that is the interface between the liquid and air, are bound together by a weak force. This force makes the liquid form a layer and is caused due to the cohesive force between the molecules of the liquid. The example phenomenon of surface tension that we can observe is surface tension and droplets. As you can see here, surface tension is responsible for the shape of the liquid droplets. Although it is easily deformed, droplets of water tend to be pulled into a spherical shape by the cohesive forces of the surface layer. Next example is surface tension and bubbles, and also surface tension and water strider. Because of this property, certain insects can withstand on the surface of water. Next is elastic modulus. Stress. Stress is the ratio of the magnitude of external force F to the cross-sectional area. The formula for stress is sigma is equal to force over area. Strain. Strain is the ratio of the change in length to the original length. So the formula for strain is epsilon is equal to elongation over original length. Elastic modulus. Elastic modulus for tensile stress is called Young modulus. Young modulus is the ratio of the tensile stress to tensile strain. So this is the formula for Young modulus, which is stress over strain. So force times with the original length over area times with the elongation. Young modulus also can be taught as the resistance in deformation. Next is compressibility of fluid and vapor pressure. Compressibility is change in volume, V, of a substance that is subjected to a change in pressure on it. The usual quantity used to measure this phenomenon is bulk modulus of elasticity, E. So the formula for compressibility is bulk modulus is equal to negative delta pressure over delta V per V. And the unit for bulk modulus is PSI. As stated before, as I said earlier, liquids are very slightly compressible, indicating that it would take a very large change in pressure to produce a small change in volume. Thus, the magnitude for E for liquid, as shown in table 1.3, are very high. The term bulk modulus is not usually applied to gases, and the principle of thermodynamics must be applied to determine the change in volume of a gas with a change in pressure. Vapor pressure. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid state. Liquid molecule at the surface escape into the gas phase. This particle created pressure above the liquid in a closed container. Let's move to part B, dimensional analysis and modeling. I will explain about dimensions and dimensional homogeneity first. Okay, first, dimensions and unit. Dimensions is a property that can be measured or calculated by multiplying or dividing other dimensions. There are 7 primary dimensions, which are length, mass, time, electric current, luminous intensity, temperature, and amount of substance. The unit for length is meter, and unit for mass is kilogram, unit for time is second, unit for electric current is ampere, the unit for luminous intensity is candela, and the unit for temperature is Kelvin, and unit for amount of substance is mole. These 7 are the primary dimensions. Okay. For non-primary dimensions, it can be formed by a combination of the 7 primary dimensions. Some of the examples for non-primary dimensions are velocity, force, density, pressure, and viscosity. Next is dimensional homogeneity. Dimensional homogeneity is the quality of an equation having quantities of same units on both sides. Law of dimensional homogeneity said every additive term in an equation must have the same dimension. If the dimensions of each term on both sides of an equation are the same, then the equation is known as dimensionally homogeneous equation. Some of the dimensional formula. For example, area, the dimensional formula is L squared. For volume, the dimension is L cubed. Density is mL power negative 3. For velocity, the dimension is LT power negative 1. For acceleration, the dimension is LT negative 2. Force, is mlt power negative 2, and for pressure, the dimension is ml power negative 1 t power negative 2. For example, S equal ut plus half at squared. So for the dimension of S is L, the dimension for ut is lt power negative 1, and t times with t, which equals to L, and the dimension for half at squared is, for half is dimensionless. The dimension for acceleration is lt power negative 2 times with t squared is t squared. So equals to L. The dimension for both sides are the same. Then the equation is known as dimensionally homogeneous equation. Next is dimensional analysis and similarity. Dimensional analysis is a mathematical technique used in a research work for designing and conducting model tests. In most experiments, to save time and money, tests are performed on a geometrically scaled model rather than on full-scale prototype. In such cases, care must be taken to properly scale the results. We introduce here a powerful technique called dimensional analysis. There are three primary purposes of dimensional analysis. First is to generate non-dimensional parameters that help in the design of experiments, physical or numerical, and in the reporting of experimental results. Next is to obtain scale laws so that prototype performance can be predicted from model performance. Next is to predict trends in the relationship between parameters. There are three types of similarity: geometric similarity, kinematic similarity, and dynamic similarity. First is geometric similarity. For geometric similarity, it concerns the length dimension. The model must be the same shape as the prototype, but may be scaled by some constant scale factor. All the angles, flow directions, and the orientations of the model and the prototype with respect to surroundings must be identical. Next is kinematic similarity, which concerns the velocity dimension. The velocity at any point in the model flow must be proportional by a constant scale factor to the velocity at the corresponding point in the prototype flow. It requires the model and prototype to have the same length scale ratio, time scale ratio, thus the velocity scale ratio will be the same for both. Next is dynamic similarity, which concerns the force dimension. When all forces in the model flow, scaled by a constant factor, is proportional to the corresponding forces in the prototype flow. It requires the model and prototype to have the same length scale ratio, time scale ratio, and the force scale ratio. In general flow field, the complete similarity between model and prototype is achieved only when there is geometric, kinematic, and dynamic similarity. The method of repeating variables and the Buckingham Pi Theorem. I will explain about the methods of dimensional analysis, which is Buckingham Pi Theorem. Buckingham Pi Theorem is a technique for finding non-dimensional parameters for a given experiment. If there are n-dimensional variables in a dimensionally homogeneous equation described by J fundamental dimensions, they may be grouped in K equals n minus J dimensionless group. Each dimensionless group is called pi. For n is number of dimensional variables, J is number of primary dimensions, K is number of dimensionless groups. The relation among the dimensionless groups will be written as follows. First is function of pi 1, pi 2, pi 3 until pi k equals 0, or pi1 is a function of pi2, pi3 until pi k, or pi2 is a function of pi1, pi3 until pi k. All these presentations are similar. This method is also known as method of repeating variables. The method of repeating variables. As an illustration of the Buckingham Pi Theorem, let's take the case of drag force on a smooth sphere. Okay, step 1 consists of listing the parameter in the problem. The drag force of a smooth sphere is mainly influenced by the sphere diameter d, fluid velocity v, fluid density rho, and fluid viscosity mu. There are 5-dimensional variables in this case, thus n equals to 5. Or we can also write it as drag force is equal to functions of d, v, rho, mu. Step 2 consists of listing the primary dimensions of each parameter. To obtain the dimension of a parameter, sometimes it is easier to start by obtaining its unit first. Okay, from the unit, the translation to the dimension can be easily done. The unit for drag force is Newton or kilogram meter per second square. M represents the dimension for mass, L represents the dimension for length, T represents the dimension for time. Then, the dimension for drag force is mLT power negative 2. The unit for diameter is m, then its dimension is L. The unit for velocity is meter per second. The dimension is LT power negative 1. The unit for density is kilogram per meter cube. Dimension is mL power negative 3. The unit for viscosity is kilogram per meter second. Then its dimension is mL power negative 1 T power negative 1. Here, we can observe that there are only 3 primary dimensions involved in all parameters, which are m, L, and T. Thus, J is equal to 3. Next, step 3 is calculate the number of dimensionless groups. Having n equals 5, j equals to 3, then the number of dimensionless groups, k, is equal to 5 minus 3 equal to 2. And then the 2 dimensionless groups are pi1 and pi2. Step 4, choose j repeating variables. There is a hint. It is generally advantageous to choose primary variables that relate to mass, geometry, and kinematics. Among these parameters, the one that related to mass is the fluid density. The one which is related to geometry is sphere diameter. And the one which is related to kinematics is fluid velocity v. So the repeating variables are rho, d, and v. Step 5 is construct the dimensionless groups. Each of pi must contain the 3 repeating variables, and we add to each pi each of the remaining variables. So, pi1 and pi2 are both dimensionless groups. So, for this, we put powers for each of the repeating variables. Let's put a1 and a2 as the power for rho, b1 and b2 as the power for d, and c1 and c2 as the power for v. So, our pi are pi1 equals rho power a1 times d power b1 times v power c1 times f. And pi2 equals to rho power a2 times d power b2 times v power c2 times mu. Let's solve for pi1 first. Pi1 is dimensionless group. we can say that its dimension is m power 0, l power 0, t power 0. And then we replace rho with its dimension. So we replace rho with its dimension. Rho is m l power negative 3 power a1, and we replace d with its dimension, v with its dimension, and f with its dimension. We rearrange this by dimensions and then sum up the power for each dimensions. We obtain three equations with three unknowns. These equations can be easily solved. Then we got a1 is equal -1, c1 equals to -2, b1 equals to -2. And then we replace the power coefficient in the pi1 with these values. After we replace in pi1, we got pi1 is equal rho -1, d power -2, b power -2 times with f. And the final expression for pi1 is f over rho b squared d squared. Now, let's work on pi2 just like what we did with pi1. So pi2 is dimensionless. We can say that its dimension is m power 0, l power 0, t power 0. And we replace rho with its dimension. We replace. And then we replace d with its dimension, b with its dimension, and mu with its dimension. And then we rearrange this by its dimension. And then we sum up the power for each dimensions. And we got three equations with three unknowns, and we can easily get the value. A2 is equal to -1, C2 equals to -1, B2 also equal to -1. And then we replace the power coefficient in the pi2 with this value. So we got pi2 equals to rho -1, d power -1, v power -1, mu. And the final expression for pi2 is equal to mu over rho vd. We know that rho vd over mu is Reynolds number. Hence, pi2 is equals to 1 over Reynolds number, or Reynolds number power -1. Step 6 is write the final functional relationship. We have both expression for pi1 and pi2. By taking the relationship in the form of pi1 is a function of pi2, then the final relation is f over rho v squared d squared is a function of 1 over Reynolds number. So the relation for drag force on a smooth sphere is f over rho v squared d squared is a function of 1 over Reynolds number. Next is dimensionless terms. Dimensionless terms are numbers which are obtained by dividing the inertial force by viscous force or gravity force or pressure force or surface tension force or elastic force. As this is a ratio of one's force to other, it will be a dimensionless number. These are also called non-dimensionless parameters. So, dimensionless terms, these are some common variables and dimensionless groups in fluid mechanics. The example for dimensionless terms, we have Reynolds number, Froude number, Euler number, Cauchy number, Mach number, Sturhalt number, and Weber number. For example, Reynolds number is generally of importance in all types of fluid dynamics problem. So the dimensionless group for Reynolds number is rho VL over mu. And the interpretation is inertial force over viscous force. This is the sources that I refer to. I think that is all from me. I hope you guys understand and enjoy watching my video. Thanks for watching and have a great day. Thank you.